Okay, so we talked about sigma notation. Now we're going to create sigma notation from data. So we already know from the last one that I is our index, n is the upper limit, m is the lower limit. This means a summation of some series, right? In this case, we've already done a series. I'm going to erase this. This was just an example. So we'll get rid of that. That was just an example of a series. Here we have some data, and we got to create our sigma notation from this data. Okay, we can go on the assumption that we're probably working with, starting at 1 and going from there. So what we're going to do is we're going to place numbers counting 1 to see how many numbers are in the series. So how many times it goes up. So 1, 2, 3, 4, 5, 6. There are 7 terms in this series. Okay. Do you see any similarities between the term itself and the actual value of the
multiple of itself equals that number?
Okay. So how would I create? What would I multiply 1 by to get 1?
1.
Okay. So let's do some permanent. And what would I multiply 2 by to get 4?
2.
Yeah. 3 by?
3.
So what do you think is happening here?
It's doubles.
How do I represent that mathematically?
The root.
Root's the opposite of it. 4 would be 4, 5 would be by 5. Yeah, power of what?
2.
2, that's right. So in this series, we usually use I or x for a variable, but in our series, our index I, that's going to be our term. So the red part, 1, 2, and we go all the way up to 7. That's what I is going to represent. And what's happening to that I is it's continuously being squared. Okay, so the sum of that summation is I. What's the lower limit?
1.
That's right. And with the upper limit?
7.
There you go. So here we go. We have our sigma notation. This is it right here. Okay, it's being squared. The value in the series is being squared. The lower limit is 1 and the upper limit is 7. Okay, we always try to relate the number of terms to what the actual value is. Does that one make sense?